Now we have to pull off the same trick for the second vector, the vector that had a magnitude of 7 in a direction of 60 degrees with the horizontal. Well, we're going to use the same trick of breaking the vector into components. By the way, if you had trouble when you tried to work this problem out on your own the first time, if you didn't get very far, maybe now you can kind of see the approach that we should use. So if you didn't finish this problem the first time that I gave you the opportunity, maybe you should pause the video now and now try to break this vector into components and finish off the problem. So if you weren't able to finish off the problem before, maybe you can now. So maybe you should pause the video and try to complete the problem now. Well, we're going to need to break this vector into components. We know that the components should be parallel to the axes that we've chosen. So we're going to have a horizontal and a vertical component, and we're going to have a right triangle with the overall vector as the hypotenuse. And of course, we'd like our right triangle to include this angle that we've been given. Here's a right triangle whose legs are parallel to our axes. We need to put arrows on the components. We always need to put arrows on the components. Well, the overall vector here was pointing up and to the right. So the horizontal component is to the right, and the vertical component is up. Now we have to figure out the horizontal and vertical components for this vector using the same approach as before. I'm going to erase the work that I used for the first vector so it doesn't confuse me when I go on to the second vector. So I've erased all the work that I did on the first vector. All I've left is the results, which are the components. And now we're going to do some work on this other vector. Well, we can use asterisks to show the side we were given and the angle that we're focusing on. And as usual, we can label the hypotenuse, adjacent, and opposite sides. To find the adjacent side, we multiply the hypotenuse times the sine or the cosine. Well, cut. Adjacent side refers to the cosine. Now we're using the cosine of 60 degrees. Not 30 degrees anymore, but 60 degrees. Now the hypotenuse is 7. We can do this in one step on our calculator. 7 times the cosine of 60 is 3.5. Exactly 3.5. So this adjacent side has a length of 3.5. We have to indicate its sign. Well, this component is pointing to the right, which is our positive direction. So this horizontal component is positive 3.5. We got one more component to work out. The opposite side. Remember, so, the sine refers to the opposite side. The length of the hypotenuse is 7. We have 7 times the sine of 60. Doing that in our calculator, we would get the number 6.1. This vertical component has a length of 6.1, and what's its sign? Well, it's pointing up, which is our positive direction. So it's positive 6.1. You can see that on this problem, as I already mentioned, I haven't invented any new variables to represent the various components. I'm just referring to them as adjacent and opposite. If you wanted to invent some variables to represent the different components, that would be perfectly okay as well. Maybe in some ways that would be better. Well, what we've done so far is we've used one of the two main skills that we learned in these videos. Remember that one of the main skills that we learned is how to take overall vectors and break them into components. We've learned how to take overall vectors and break them into components. So we took this overall vector of length 5 and we broke it into its components, positive 4.3 and positive 2.5. And then we took this overall vector of length 7 and we broke it into its horizontal and vertical components, positive 3.5 and positive 6.1. Of course, the technique that we use for that is trigonometry. One of the components will be represented by the adjacent side of the triangle, and one of the components will be represented by the opposite side of the triangle. So then we can use these two formulas to work out the two components. And a nice thing that you might have noticed is that this does not require really any algebra at this point. Remember that if you ever forgot these two equations, you could go back to the original definitions of sine and cosine. Cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. If you cross-multiply those equations, you'll get these equations, which are our standard equations for finding components. All right, so this was a review of one of the main skills we've learned in these videos, going from the overall vector to the components. So I hope that you found it very easy to break these vectors into components. If you didn't find it easy, then make sure you do a lot more practice until this skill is easy. Why did we want to know the components in the first place? Well, remember what we're trying to figure out is the overall length of this displacement vector here. How far is our final position from our initial position is what we want to know. And remember, we couldn't just add the 5 and the 7 and get 12, because the 5 and the 7 represent vectors that are pointing in different directions. If you walk for 5 meters in one direction, and then you walk for 7 meters in a different direction, there's no reason to think that you're going to end up 12 meters from where you started. So we can't just add the 5 and the 7 because those vectors are not parallel. The reason we wanted to get the components is because the components are parallel to each other, so we can add them directly. For example, what is our total horizontal displacement? What's our total horizontal displacement from where we started? Our total horizontal displacement from where we started. Well, first we went 4.3 meters in the positive horizontal direction, and then we went 3.5 meters in the positive horizontal direction. Well, we can definitely just add these two horizontal movements together because they're both parallel. They're both horizontal. If you go 4.3 meters in the horizontal direction and then you go 3.5 meters in the horizontal direction, you can just add those two numbers together to get your overall horizontal displacement. Looks like that would be 7.8. Positive 7.8. Let's continue to indicate signs here. Positive 4.3 plus positive 3.5 is positive 7.8. So we've gone 7.8 meters total in the horizontal direction here. Our overall horizontal displacement has been positive 7.8. First 4.3 meters to the right, and then another 3.5 meters to the right. You can see how easy it is to add horizontal components because they're parallel to each other. Now, how about our vertical displacement? Well, first we went 2.5 meters up, and then we went another 6.1 meters up. 2.5 meters up, and then another 6.1 meters up. It should be pretty clear we can just add those two together and get our total vertical displacement. Since this is a vertical displacement and this is a vertical displacement, we can just add them directly to get the total vertical displacement. Positive 2.5 plus 6.1 equals positive 8.6. If you go 2.5 meters up and then another 6.1 meters up, your total displacement up is 8.6 meters, just 2.5 plus 6.1. So our total vertical displacement here is 8.6 meters. Horizontally, we're 7.8 meters to the right of where we started. And vertically, we're 8.6 meters above where we started. Horizontally, we're 7.8 meters to the right of where we started. And vertically, we're 8.6 meters above where we started.